Let's extend the definition of exponents to include integer exponents. Informally, positive integer exponents denote repeated multiplication. The formal recursive definition of positive integer exponents capitalizes on this repeated multiplication idea. Let's first review the laws of exponents and then follow up with a variety of examples. The first law states that when we multiply like bases, we add the exponents. The second law states that to divide like bases, we subtract the exponents in order of top exponent minus bottom exponent. To raise a power to a power, we multiply the exponents. To raise a product to a power, we apply the exponent to each factor. And finally, to raise a quotient or fraction to a power, we apply the exponent to the numerator and to the denominator. We comment here that exponents do not distribute over sums or differences. Now let's consider the exponent 0. How would we define a raised to the 0 power? For any non-zero a, we define a to the 0 power to be equal to 1. Why is this the correct definition? Suppose we want to discover the value of 2 to the 0. Let x equal 2 to the 0 and use the law of exponents. 2 to the 0 times 2 to the third will equal 2 to the 0 plus 3 using multiplication of like bases property. So 2 to the 0 times 2 to the third will equal 2 to the third. Substituting x for 2 to the 0 and 8 for 2 cubed, we have that x times 8 equals 8, and therefore x equals 1. Thus, 2 to the 0 equals 1. Similarly, for any non-zero base a to the 0 must equal 1. Now let's move to the definition of negative integer exponents. For non-zero a and for positive n, a raised to the power of negative n is defined to be the reciprocal of a to the n power. Why is this the correct definition? Could we have defined negative exponents differently? Well, suppose we want to discover the value of 2 to the negative 3 power. Let's let x equal 2 to the negative 3 power and use the law of exponents. Then 2 to the third power times 2 to the negative third power will equal 2 to the 3 plus negative 3 power. Again, we've used when you multiply like bases, you add the exponents. So 2 cubed times 2 to the negative 3 will equal 2 to the 0. Let's substitute 1 equal 2 to the 0 and x equal 2 to the negative 3. And we have that 2 cubed times x is 1. Therefore, x has to be 1 over 2 cubed. Thus, 2 to the negative third power is the reciprocal of 2 to the third power. Now we can use these definitions and the laws of exponents to simplify expressions with negative integer exponents. Let's consider some example problems. 4 raised to the minus 2 power equals 1 over 4 squared, which equals 1/16. Consider the fraction 3/5 raised to the minus 2 power. The negative exponent means reciprocate, so we have 5/3 squared. Applying the exponent to the numerator and denominator, we get 5 squared divided by 3 squared, which simplifies to 25/9. Now let's consider a negative fraction raised to a negative exponent. The negative exponent means reciprocate, and the reciprocal of -2/3 is -3/2. Now applying the exponent of 3 can be interpreted as multiplying 3 factors of -3/2. Thus we get a negative 27/8. Consider the fraction 1 over x to the -5. Since the numerator is 1, and 1 raised to any power is 1, we can rewrite this as 1 over x raised to the -5 power. The negative exponent means to reciprocate, and the reciprocal of 1 over x is x. Therefore, we get x to the 5th. Looking back at the first and last examples, we see that a negative exponent moves a factor between the numerator and denominator. 4 raised to the -2 power on top of the fraction moves a 4 squared to the bottom of the fraction. Similarly, an x to the -5 on the bottom of a fraction moves x to the 5th to the top. More examples will help clarify this. Let's consider -2 times x to the -4. The -4 power means reciprocate, but notice that the power only applies to the x and not to the coefficient. So we get -2 times 1 over x to the 4th, which equals -2 over x to the 4th. Recall that a negative fraction can be written with the minus sign in front of the fraction, or in the numerator, or in the denominator. Now let's find the sum of 2 to the -1, 4 to the 0, and 3 to the -2. Using the definition of integer exponents, this equals 1/2 plus 1 plus 1 over 3 squared. To add 1/2 plus 1 plus 1/9, we need common denominators. Rewriting each fraction with a common denominator of 18 and adding the numerators, we get 29/18. Let's consider a slightly more complicated fraction with numerator x cubed times x to the -8 and denominator x to the 4th. We can multiply the like bases in the numerator by adding the exponents to get x to the -5 over x to the 4th. Now we can divide like bases by subtracting the exponents, producing x to the -9th. Only in the final step do I eliminate the negative exponents by reciprocating to get 1 over x to the 9th. Let's consider one final complicated example. To clarify the problem, I'm going to write the constants in black, the x factors in red, and the y factors in blue, and I'm going to explicitly write x as x to the 1. Also, we can simplify the fraction before dealing with the outer exponent of -2. So I divide like bases by subtracting the exponents. The power on x is -3 minus 1, and the power on y is -2 minus a -3. Simplifying the exponents produces 3 times x to the -4 times y to the 1 over 4, with that fraction raised to the -2 powers. There are multiple options on how to proceed now. I will apply the -2 power to the numerator and denominator. In the numerator, the -2 power applies to all 3 factors. Raising powers to powers requires multiplication of the exponents. Now, the negative exponents move factors from top to bottom or vice versa, producing 4 squared x to the 8th over 3 squared y squared. This reduces to 16x to the 8th over 9y squared. Take a few minutes to rework this problem with paper and pencil. It is definitely possible to perform many of the steps in a different but legitimate order and arrive at the correct simplification.